One of the first things we did with the electric field was find the electric field from a point charge. Once we had that, we could use that to help us find electric fields from charge distributions and more complicated scenarios. So let's do that for electric potential. Find the electric potential due to a point charge. We're going to start with the equation we ended up with last time. The change in potential is negative the integral of E dot ds. And I'll say it again, we use this equation a lot, finding electric potential. A point charge fills the space around it with an electric field. And we want to move from point A to point B. We know what the electric field is due to a point charge. K Q over R squared. This is a charge Q. So let's go back up to our potential equation. The change in potential, delta V, is going to be our final potential minus our initial potential. That's delta V. And that has to equal negative the integral of E dot ds. Now I'm going to try really hard to get my minus signs correct, because if you do everything properly, this will give you the right sign for the delta V. But sometimes it's a little tricky. So I always tell my students, try to get the minus signs right. But in the end, just think about it for a second and make sure you got it right. And if you didn't, fix it at the end. So that's what I'm going to do here. Final minus initial on my potentials is equal to negative the integral of E dot ds. So that's going to be the magnitude of my electric field, the magnitude of ds, and the cosine of the angle you get when you put their tails together. In this case, we're moving from A to B. So my ds is just equal to dr. I'm moving out in the radial direction. My electric field also points in that direction. That means that I get a theta when I look at these two vectors. When I put their tails together, I get a 0-degree angle. So the dot product is going to have a cosine of 0 degrees in it, which is just 1. Now I can plug in my electric field. I know the electric field in this region of space is K Q over R squared. My ds is just dr, and my cosine theta is just 1. And I'm integrating from my initial position, I'll call that RA, to my final position out here, I'll call that RB. The integral of 1 over r squared is negative 1 over r, and I'm evaluating this from RA to RB. The minus signs cancel. I have a 1 over RB minus 1 over RA. So I tried to get all my minus signs right. I thought about it. I tried to get the cosine theta correct and my limits correct and all of that. Let's see if I got it right in the end. I know that the potential at point B has to be, what does it have to be when comparing it to the potential at point A? It has to be less because my electric field is pointing from A to B. My electric field points in that direction. And the electric field always points toward lower electric potential. So the potential at point B must be less than A. That means the left side of my equation is negative. If VB is less than VA, then when I do the math, when I subtract the potential at A from the potential at B, I get a negative number. Let's look at the right side. This is also negative because the radius at B, the distance that B is from my point charge, is greater than the distance of A. So 1 over B is smaller than 1 over A, so I get a negative number. Everything checks out. I've got negative on the left side of my equation. I've got negative on the right side of the equation. So everything checks out. I'm good to go. I can go on to the next step. I don't have to correct the sign. If one side of my equation was negative and the other side was positive, I would fix it here by adding a negative to one side. Electric potential, although it is not electric potential energy, it's electric potential. There's a difference. But like potential energy, what really matters is the change. Delta V is what's important. Telling me that the voltage is 100 volts somewhere doesn't really help me. But telling me that the potential is 100 volts higher at point A than at point B, that tells me something. Delta V is what's important. The change in electric potential is what's important. So we need to take a reference to something. That's why this equation is a little cumbersome the way it is. It's looking at two different places, A compared to B. If we could all agree on using the same reference location, then we could just write it as a single value. So let's see, where does the potential naturally want to go to zero? It naturally goes to zero as R goes to infinity because it's a 1 over R dependence. Since the potential naturally wants to go to zero at R goes to infinity, let's just all agree that when we're talking about point charges, we're just going to assume the potential is zero at infinity. If we all agree, then we can write this equation, VB goes to zero, and we end up with the potential at point A is KQ over RA. I'm just going to leave the subscripts off. This is the potential some point R away from a point charge. If we all agree that the potential is zero at infinity. Now we have the potential from a point charge. Before we do anything with that, let's talk a little bit about units. The units are volts. And 1 volt is a joule per coulomb. Our units for electric field up until now have been newtons per coulomb. Now that we have another definition, we can write it in terms of the volt. A volt per meter. Those are both acceptable units for electric field. For some reason, people get very sloppy in their terminology when they're talking about potential. I'm sure I've already done it in this video. I've referred to it as voltage. We don't do that with anything else. I don't say what's the Celsius outside today. I say what's the temperature outside today. Celsius is the units we use for temperature. But for some reason, we kind of get sloppy and we don't say what's the electric potential at this point. We say what's the voltage at this point. So I'll try not to do that, but you have to accept the fact that everyone does it.